Imagine a world where compasses spin wildly, no longer pointing north. This unsettling scenario is not just a figment of our imagination, but a potential reality if the Earth's magnetic field continues to weaken. The magnetic field, which has been our planet's guiding force for millennia, is showing signs of distress. This invisible shield, generated by the movement of molten iron in the Earth's outer core, is crucial for navigation and much more. The aurora borealis, once confined to the polar regions, paints the sky in vibrant hues across the globe. These stunning light displays, caused by charged particles colliding with our atmosphere, could become a common sight far from the poles. While beautiful, this phenomenon is a sign of the magnetic field's weakening grip on these particles, allowing them to penetrate deeper into our atmosphere. Migratory animals lose their way, their internal compasses thrown into disarray. Birds, whales, and other creatures that rely on the Earth's magnetic field for navigation could find themselves lost, unable to complete their long journeys. This disruption could have cascading effects on ecosystems, as these animals play crucial roles in their environments. This is not a scene from a science fiction movie. It's a glimpse into a future where Earth's magnetic field has weakened and reversed. Such a reversal, known as a geomagnetic reversal, has happened many times in Earth's history, but the process is slow and can take thousands of years. However, the weakening we are observing now is happening at an unprecedented rate. Our planet's magnetic field is not static. It's a dynamic force that has fluctuated throughout Earth's history. These fluctuations are recorded in the geological record, showing a pattern of reversals and changes. The magnetic field is generated by the geodynamo process in the Earth's core, where the movement of molten iron creates electric currents that produce the magnetic field. Scientists have observed a gradual weakening of the magnetic field over the past century, with the most significant dip occurring in a region known as the South Atlantic Anomaly. This area, stretching from South America to Africa, has seen a dramatic decrease in magnetic strength, causing concerns about increased radiation exposure and its effects on satellites and other technologies. This weakening has led to speculation about an impending magnetic flip, an event that could have profound implications for life on Earth. A magnetic flip, where the north and south magnetic poles switch places, could disrupt navigation systems, animal migration patterns, and even the behavior of the atmosphere and climate. The Earth's magnetic field is our invisible shield, protecting us from harmful solar radiation and cosmic rays. Without this protective barrier, life on Earth would be exposed to dangerous levels of radiation, which could increase the risk of cancer and other health issues. The magnetic field also helps to maintain the atmosphere, preventing it from being stripped away by solar winds. It acts as a barrier, deflecting these charged particles away from our planet. This deflection is crucial for maintaining the delicate balance of our environment, as increased radiation can have harmful effects on both living organisms and technological systems. A weakened or reversed magnetic field could expose us to higher levels of radiation, potentially impacting our health, technology, and the delicate balance of our planet's ecosystems. Increased radiation could disrupt communication systems, damage satellites, and even affect power grids. The potential consequences of a weakened magnetic field are vast and far-reaching, making it a critical area of study for scientists around the world. Deep within the heart of our planet lies a molten iron core, constantly churning and generating electric currents. This core is composed primarily of iron and nickel, and its movement is crucial for the creation of our planet's magnetic field. The intense heat and pressure in the core cause the iron to remain in a liquid state, despite the immense gravitational forces trying to solidify it. This dynamic environment is the powerhouse behind one of Earth's most vital features. This dynamic core acts like a giant dynamo, creating the Earth's magnetic field. The process, known as the geodynamo, involves the movement of molten iron within the outer core, which generates electric currents. These currents, in turn, produce magnetic fields that combine to form the overall magnetic field of the Earth. This field is not static, it fluctuates and changes over time, influenced by the complex motions within the core. Imagine a bar magnet at the center of the Earth with invisible lines of magnetic force extending out into space. These lines, known as magnetic field lines, emanate from the magnetic poles and loop around the planet. They create a protective shield that extends thousands of kilometers into space, forming the magnetosphere. This magnetosphere is essential for life on Earth as it deflects harmful solar radiation and cosmic rays. These lines form a protective bubble around our planet, shielding us from the constant bombardment of charged particles from the sun. Without this magnetic shield, these particles, known as the solar wind, would strip away our atmosphere and expose the surface to intense radiation. The magnetosphere acts as a barrier, redirecting the solar wind and preventing it from reaching the Earth's surface. The magnetic field is most concentrated at the poles where the magnetic field lines converge. This convergence creates regions of intense magnetic activity, known as the polar cusps. These areas are where the magnetic field lines are closest together, and they play a crucial role in the interaction between the solar wind and the Earth's magnetosphere. This concentration is what gives rise to the spectacular auroras, also known as the northern and southern lights. When charged particles from the solar wind collide with atoms and molecules in the Earth's atmosphere, they excite these particles, causing them to emit light. This light is what we see as the beautiful, dancing colors of the auroras. The specific colors depend on the type of gas being excited. For example, oxygen produces green and red lights, while nitrogen produces blue and purple hues. Charged particles from the sun are channeled along the magnetic field lines towards the poles where they interact with the Earth's atmosphere, creating breathtaking displays of light. These interactions occur at altitudes ranging from 80 to 500 kilometers above the Earth's surface. The auroras are not only a visual spectacle, but also a reminder of the dynamic relationship between our planet and the sun. The magnetic field's influence extends far beyond the auroras. It reaches out into space, forming the magnetosphere, which acts as the first line of defense against solar and cosmic radiation. The magnetosphere is shaped by the solar wind, creating a bow shock on the side facing the sun and a long tail on the opposite side. This structure helps to protect not only the Earth's atmosphere but also satellites and other space-based technologies. It plays a vital role in protecting our atmosphere from being stripped away by solar wind, a stream of charged particles constantly flowing from the sun. The magnetosphere deflects these particles, preventing them from eroding the atmosphere and causing significant damage to the surface. This protection is crucial for maintaining the conditions necessary for life on Earth. Without the magnetic field, Earth's atmosphere would be vulnerable to erosion by the solar wind, potentially leading to a scenario similar to Mars, where a once thicker atmosphere has been reduced to a thin veil. Mars lacks a global magnetic field, which has allowed the solar wind to strip away much of its atmosphere over time. This comparison highlights the importance of Earth's magnetic field in preserving our planet's habitability and protecting it from the harsh conditions of space. Earth's magnetic field is not a constant. It has flipped hundreds of times throughout our planet's history. These flips, known as geomagnetic reversals, are fascinating phenomena that have intrigued scientists for decades. The magnetic field, generated by the movement of molten iron in Earth's outer core, acts as a protective shield against solar and cosmic radiation. However, this shield is far from stable. Scientists can track these flips by studying the magnetic signatures preserved in ancient rocks. These rocks, often found in volcanic regions, contain minerals that lock in the direction of the magnetic field as they cool. By analyzing these magnetic signatures, researchers can reconstruct the history of Earth's magnetic field. When molten lava cools and solidifies, iron-rich minerals within the rock align themselves with the Earth's magnetic field, creating a permanent record of the field's direction at that time. This process, known as thermoremnant magnetization, is crucial for understanding past magnetic fields. Each layer of rock tells a story, capturing a snapshot of the magnetic field's orientation. By studying these magnetic records, scientists have pieced together a timeline of Earth's magnetic field reversals. This timeline reveals patterns and anomalies that help us understand the dynamics of our planet's core. Advanced computer models and simulations are used to predict future reversals and understand the underlying mechanisms driving these changes. These reversals are not regular events. They occur at irregular intervals, averaging about every 200,000 years. However, the timing is unpredictable, with some periods experiencing frequent flips and others going millions of years without a reversal. This irregularity adds to the complexity and mystery of geomagnetic reversals. However, the last reversal occurred approximately 780,000 years ago, suggesting we might be overdue for another flip. This long period without a reversal has led some scientists to speculate about the current state of Earth's magnetic field and whether we are on the brink of another significant change. During a magnetic flip, the magnetic field weakens, becomes more complex, and may even disappear entirely for a short period. This weakening can have significant implications for life on Earth, as our planet's magnetic shield is crucial for protecting us from harmful solar radiation. The temporary loss of this shield could lead to increased radiation levels, affecting both technology and biological systems. The magnetic poles wander and eventually switch places, with the magnetic North Pole becoming the magnetic South Pole and vice versa. This process, known as a geomagnetic excursion, can take thousands of years to complete. During this time, the magnetic field can exhibit erratic behavior, with multiple poles appearing at different locations on the globe. These flips are not instantaneous events. They can take hundreds or even thousands of years to complete. The gradual nature of these reversals means that the magnetic field can remain in a state of flux for extended periods, leading to prolonged periods of weakened magnetic protection. Understanding these processes is essential for preparing for future changes and mitigating potential impacts on our technology and environment. The Earth's magnetic field is intimately linked to the movement of our planet's tectonic plates. The Earth's outer layer, known as the lithosphere, is broken into several large plates that constantly move and interact with each other. These plates float on top of the Earth's mantle, a layer of hot, viscous rock. The movement of these plates is driven by convection currents in the mantle, which are generated by the heat from the Earth's core. As the plates move, they can affect the flow of molten iron in the outer core, influencing the generation of the Earth's magnetic field. Some scientists believe that major tectonic events, such as the formation of supercontinents, could trigger magnetic field reversals. The exact mechanism linking plate tectonics and magnetic field flips is still an area of active research, but the connection highlights the interconnectedness of Earth's systems.